Okay, well, today I'm not going to go through the full vector review, but I'm going to try to just emphasize some of the things I think are important, some of the things that can be a little trickier. Um, and then I guess on Friday, if you have questions about any of the homework problems, I probably won't get to those today, I don't think, because I'm just trying to get to the point where, get to a certain point in concepts. Um, But on Friday, if you have any questions, I'd be happy to go through any homework questions. Um, okay, so vector review. This stuff is going to be so important for how this class goes. Um, so, make sure you take this stuff seriously. I know that you've seen vectors before, and that makes, I think, it's sort of a natural thing to be like, I don't have to pay that much attention to this. Maybe you don't, but making sure that this stuff is solid is going to be important for how this class goes, you know. Um, okay, so first of all, we're going to use a different notation this semester than what you've seen before. The notation that that people tend to use in physics is like this. And we are going to represent that vector in a column matrix like this. So that top element is the first component, the middle element is the second component, bottom element is the third component. Um, and when we're doing stuff in the plane, which we're going to do pretty often, calculations in the XY plane, um, in physics, you would have written these vectors as AI plus B times J. Um, and we'll represent that as AB like this, where you just leave off the third element, or that's equivalent to this. So sometimes we'll have to make the change to this in order to do calculations. Okay, so always recognize that those two are the same thing, whether you put that third element on or not. um, okay, so this is the X component. This is the Y component. And this is the Z component. Um, in order to visualize vectors, notice that you can always think of the vector with its tail at the origin. Um, and if you do that, then the vector components, let me write vector components. Are the coordinates of the vector's head. Okay, so for example, what does the vector 6, -4 look like? Well, if you imagine a vector with its tail at the origin, I'll make this the X and this the Y. then all you're doing is plotting that point. So go out 6 in the positive x, 4 in the negative y. That point is somewhere like that. And so that vector is this. Okay? Um, so let's say, okay, so to calculate vector components in 2D, given an angle and a magnitude, find the counterclockwise angle from the positive x-axis to the vector. And I'm going to call this angle theta. Okay. And then the vector components are the length of the vector. Let's call this magnitude L for length. You go away. L times the cosine of theta, L times the sine of theta. Okay, so for example, let's say that we have a vector that has a magnitude of 1.5 and makes an angle of 30 degrees with the horizontal like that. What are the vector components and in order to give vector components, you always have to know what your coordinate system is. You know, sometimes I won't specify that or whatever, and in that case, I'm probably just assuming you're going to use, you know, x to the right and y up because that's what you're used to using. But vector components don't make any sense until you choose your coordinate system. So let's say that our coordinate system, again, is going to be just the standard x this way and y this way. Okay, so I'm going to draw out the coordinate system. And I'm going to put the tail of the vector at the origin. That's important. You'll get wrong answers if you don't do that. There's the vector. This angle is 30 degrees. This magnitude is 1.5. So the counterclockwise angle from the positive x-axis to the vector, you can think of that as 30 degrees short of 180. So theta is equal to 150. So this vector is 1.5 times cosine of 150, 1.5 times sine of 150. And if you plug that into your calculator, make sure your calculator's in degrees. This gives 1.299 about, for the x component, negative and then 0.75. Of course, you can always make right triangles, think about SOHCAHTOA, calculate the lengths of those components, and then use what quadrant you're in to know what the signs are. That's what I'm doing if I'm calculating these like in my head in front of class or whatever. I'm thinking about the right triangles and stuff. But this will always work, and it's a nice systematic way to do it. It's a way that you can program, you know, like you can put this rule into your computer code, and it'll always give the right answers. So it's a nice thing to have. We're going to do a ton of vector calculations, and so you're going to want to be able to do these calculations in your calculator. So let me tell you how to enter vectors into various TI calculators. If you have an HP calculator or some other company, come talk to me and we can figure it out if you're having trouble figuring out how to do it. But most people have TI calculators, and that's what I'm most used to. So entering vectors into Texas Instruments calculators. Texas Instruments calculators are awesome. The one thing that's a little annoying is every version that they make, everything is done totally differently. So I have to sort of break this up into categories. So first of all, if you have a TI 83 or an 84 or an 86, I think most people that would be an 84, but there are 83s and 86s out there. You have to go to the matrix. Well, you don't have to actually, not in every one of these cases. This is just one way you can do it. But you can go to the matrix environment. That's like hit a second button, go to math, and that takes you to matrix. Then go to edit. Then choose your dimension. Remember, we're doing these as column matrices, so that would be either, you would either choose 2 by 1 or 3 by 1. And then you enter that value, and then you have it in the calculator. If you have an 84 or an 86 or an 89, you can also skip the whole matrix environment, and you can enter using square brackets. So you have outer square brackets that tell it that you're entering a matrix of some type. And then the inner square brackets are rows in your matrix. So you'll go like A, B, C, and then the button here, you can put this in a variable if you want. This is the store button. And then you can use those calculations. So this would be the X component, Y, and Z. If you have an 89, you can also use this format that saves a couple keystrokes. You can just go square brackets to define the matrix, and then A, semicolon, B, semicolon, C, and matrix. And then store it if you want to store it. And then the last one is if you have the inspire, there is a button that looks something like this. It's hard for me to make sense out of what this is supposed to be, but I think this is what it looks like. And then you go to the next menu that says, matrix sizes. Do you want this? Or are you doing 3D and you want this? And then click enter, and it'll just let you enter those values. And as we go through different vector calculations, I'll talk about how to do these calculations in different calculators. One that we're going to use, I would guess, 1.5 million times this semester is cross product. 89 and Inspire have a cross product built in. The other ones don't, but it's easy to program. So as we get to that stuff, if you want a program in your calculator, come talk to me and we can enter it. Okay. So let's talk about some vector calculations. The first one is adding two vectors. So if you're adding the vectors A, B, C plus D, E, F, in order to add those, all you do is add the components, the like components. So the sum of these would be A plus D for the X component, B plus E for the Y component, and C plus F for the Z component. And if you, whatever calculator you have, if you use one of these things to get two vectors entered into your calculator, and then you just use the regular addition button, it will do it this way. So all of those calculators know how to do vector addition, just using the regular addition button. Okay. Same thing with multiplying a vector by a number. All your calculators will know how to do that. So if you're multiplying a vector by a number, so say that the number is D and the vector you're multiplying is A, B, C. The output is that D times each one of those components. So the X component would be dA, the Y component would be dB, the Z component would be dC. And we're actually going to use this a lot. So this will be important to us. We're going to use it to define vectors, to break down vectors into a magnitude and a direction. So we'll use it to break vectors into a magnitude and a direction. And I'll talk about that later today. If you have a vector, let's say you have a vector u, you can always break that down into the magnitude of that vector, the length of the arrow, you can think of it, times a unit vector in the direction of the vector. So this is the magnitude. And this is a unit vector representing the direction. Well, we've actually already seen that once. If you go back up to this example, we had a vector with a magnitude of 1.5. And so in order to define the full vector, the components of the full vector, we just multiplied 1.5 times a unit vector in that direction, which was cosine of 150, sine of 150, and it gave us the components. Okay, but we're going to go in the other direction pretty often. And the reason is we're going to have vectors where we know the direction, but we don't know the magnitude. So it's a way to isolate what we know from what we don't know. And it reduces the number of variables we'll use. Okay, the next thing we'll do is multiply two vectors together. So this is what, 3? And there are two ways to do this. The first one is the dot product. Sometimes you'll see this referred to as the scalar product. Sometimes you'll see it referred to as the inner product. But if you're taking the dot product between A, B, C, and D, E, F, the answer you get out isn't going to be a vector. It's just going to be a number, a scalar. And the answer is going to be A times D plus B times E plus C times F. And the reason that it's sometimes called a scalar product is because the output is a scalar, not a vector. Okay, this one isn't going to be super important to us. It does turn out that if you have a TI-89 or a TI Nspire, there's a built-in function for this. And that function is called lowercase dot capital P. And you would just put the first vector in this side, the second vector in this side, and it would give you the dot product. Okay. The second one is going to be more important to us. We're going to use it all the time. This is the cross product. Which also you sometimes hear called the vector product. Or the outer product. And the cross product, so if you have A, B, C crossed with D, E, F. There are kind of two ways to do this by hand. The way I like to think about it is like this. So for the X component, cross those out and then take this times this minus this times this. You're doing those cross multiplications, okay? Which is, I'm sure, where the name cross product comes from. And so the X component is going to be BF minus CE. Okay? Then for the Y component, we're going to cross out these. And we're going to do this times this minus this times this. So I'm going to write this in parentheses again. This is AF minus CD. And then dealing with vectors and matrices, you'll sort of get used to this thing where the Y component has to always be a little bit of a problem, a little bit different from the other ones. In this case, we take the negative of what we got there. Okay? And then for the Z component, cross out those two Z components. It's this times this minus this times this. And so the Z component is AE minus BD. A lot of people learned this to do cross products in a way where you set up a matrix and you do a determinant of the matrix. It gives you the same answers. That would be pretty bad if it didn't. That would not be an effective way to do this calculation. But if you set up the matrix I, J, K, and then the first row is your first matrix, your first vector, and your next row is the next vector, and you take the determinant of this matrix. So cross out that row and that column, and that's going to give you this I times this. You know, you're going to take the determinant of this submatrix and multiply it by I. So this is BF minus EC. And then we'll do, for the Y component, we'll cross out this row and this column. And we'll go AF minus DC. And then for the Z component, we'll cross those out. And we'll go plus K times AE minus DB. And you can see that those give the same answer. Some people are just used to thinking about it this way. Most of the time in this class, you can get by without doing hand calculations at all, but sometimes you're going to need to do this. Yes?
For quizzes and exams, are we forced to memorize this formula?
I would recommend you memorize it, but I think I do always put it on the exams. I mean, it's just such a useful thing. Any other questions right now? Okay, what about in 2D? I want you to notice something important in 2D. So let's say that we have the cross product of the vector, let's say A, B, and then 0 because it's just in the xy plane, crossed with C, D, 0. And let's see what happens here. So for the x component, cross this out, you have 0 minus 0. And so we got 0 minus 0 for the x component. For the y component, cross out the b and the d, and you have 0 minus 0. And then for the z component, cross out the zeros, and you get AD minus BC. And this is a totally general result. It's always the case that the only non-zero component is the z component. Okay. There's a reason for that, a physical, intuitive reason for that. And that is that the cross product, the output of the cross product is always perpendicular to both input vectors. So it's always perpendicular to both input vectors. Okay, so if you have two vectors that lie in the xy plane, one vector going this direction and one vector going this direction, like parallel to the screen, the only way you can make a vector that's perpendicular to both of those is to either have it coming out of the page or into the page. Okay, and so anytime you take cross products between two-dimensional vectors, the output is going to be in that third dimension. Okay. So a lot of times, just to save writing or whatever, when we do cross products between vectors that are in the xy plane, and we're going to do that all the time, I'm going to write it down as if it's just a single number. The answer is just a single number. But remember, cross products always have a vector output. It's just that if the two vectors you're multiplying are in the xy plane, we know that the only non-zero number represents the z component. Okay. And we also know that besides being perpendicular to both of the input vectors, the direction of the output vector has to obey the right-hand rule. Okay, so let me show you how this works. So let's say that we're taking the cross product between a vector in this direction and a vector that's pointing into the page. The way people represent vectors going into the page, straight into the page, is a circle with a cross through it. I think it's supposed to represent like the arrow, the feathers of the arrow. You're seeing the feathers fly away from you, And when people want to represent a vector that's coming straight out of the page towards you, they just put a dot in the middle like you're looking right at the point of the arrow. So let's say this is our vector v. Okay, so what we're going to do is we're going to position our hand in such a way that it can start in the direction of the first vector, and then your fingers can curl to be in the direction of the second vector. And if you're like, I'm double jointed, my fingers can go either way. Pretend you're not double jointed. Don't give me shit. Okay. Pretend your fingers can only go one way. So I'm going to put my hand to start this direction. That way I can curl my fingers to go into the page. And once your hand is in that correct orientation, your thumb tells you the direction of the cross product. Okay? So let's see. Here's your hand. So start out like this. With your fingers going in the direction of you. And then, this is the moment of truth. I think I might have put an extra joint on this finger. You really are double jointed. Yeah. So now your fingers are pointing in the direction of V into the page. And so the result is up. Any questions about that? Okay, cross product. If you have a TI-89 or a TI Nspire, you're in luck. It will do the cross product for you. It will do the cross product. And this is a time saver. The notation looks like this, lowercase cross. It's pretty much the same notation as for the dot product, just lowercase cross, then a capital P, and then put in your two vectors in order, whatever they are. If you have a different TI calculator, like I said, it only takes 5 minutes or less to program the cross product, and it's probably worth doing. So just come talk to me about that. Also, I think in that textbook document that I have on D2L, in the appendices, I think it tells you for a TI-84 how to program the cross product in. So you can go to that and see if you can get it working yourself. Okay. All right, cross product is important. So there's a few things I want you to notice about the cross product. The first one is, don't forget to put the negative sign on the y component. Remember, the y component always has to be the weird one. Like the y component is like the kid who like dresses mostly trendy, but like wears two different colored socks or whatever. Like, why you just got to be a little weird all the time? Like, it's just how he is, you know. Um, the second one, I already said this, but the output of the cross product is perpendicular to both input vectors. Um, the third is the cross product of any two vectors that are parallel is 0. Um, that actually gets back to these alternate names for dot product and cross product. I said that sometimes you see the dot product called the inner product and the cross product is called the outer product. That's because in some sense, the dot product measures how close two vectors are to being in line, being parallel. And the cross product measures how close they are to being perpendicular. So if they get parallel, the magnitude goes down to 0. The fourth one, we're going to have to choose coordinate systems a lot of times in this class, and sometimes choosing the right coordinate system can simplify your work quite a bit. But you have to follow the rules of coordinate systems in order to do that. The most obvious one is the coordinate axes have to be perpendicular. But that's not the only requirement. So we always, for the math that we're using, have to use right-handed coordinate systems. And these are the requirements for a right-handed coordinate system. Uh, the cross product of the x-axis and the y-axis has to be equal to the z-axis. I'm going to leave a space for the middle one. The cross product of the y-axis and the z-axis has to be equal to the x-axis. But then the middle one says I cross k is equal to negative j. So the y-axis always has to be a little weird, you know? It's always got to do its own thing a little bit. But if your coordinate axes don't follow these rules, then it's not an acceptable coordinate system. Okay. And then there's only one more thing, but these are all worth remembering. And these are all the kind of things that get asked in quizzes. So, you know, read back through this stuff. But the last one says order matters in cross product. In the dot product, it doesn't matter, but in cross product, it does. So if you have a vector u and take a cross product with a vector v, this is actually the negative of what you would get if you changed the order. Okay. Okay, let me So the next thing we're going to talk about is forces with known directions and unknown magnitudes. Well, actually, I don't know why I said force. It's really generally true of vectors. It's just force is going to be where this comes up the most often in this class. So I'm going to change this to vectors with known directions and unknown magnitudes. Um, we're always going to break these vectors up into a magnitude times a unit vector. So we'll always break these into a magnitude times a unit vector. Um, how we calculate the unit vector is going to vary. How we calculate the unit vector will depend on the problem. Okay, so the first way we'll do this is for 2D problems, where the direction is given as an angle, we're just going to use the unit vector cosine theta, sine theta. Where theta, that's not a theta, where theta is the counterclockwise angle from the positive x-axis. Second, for 3D problems, no matter what in 3D, and in 2D problems, where you're given reference points instead of angles, um, we're going to do, we're going to define a vector that goes from one reference point to the other. So I'll write P2 minus P1. That's a vector that goes from P1 to P2. Then the magnitude of that vector we'll get using the Pythagorean theorem. So ux squared plus uy squared plus uz squared, all square root. And then the unit vector is 1 over the magnitude times the original vector. We don't have time to do example problems with this right now, but I'll do a problem at the start of class next time. Anybody have any questions about that? Okay, so I'm going to assign the rest of the vector review problems for Friday. If you have any questions about any of them, I'd be happy to work through any of those in class on Friday, and we'll do an example problem or two, and then we'll go on to actual statics. Okay, bye.